Hey there, campers. Here we are ready to start a brand new unit today. We're going to move on to EMR. There was the one last section in the workbook, 4-5 perhaps, which dealt with moving a conductor in a magnetic field. We did work on those problems, the FM equals BIL, before spring break, so we're going to jump just straight ahead to EMR and get a little bit of theory going on today. So there will be a bell work at the end, but it is just pure theory, as will tomorrow's as well. So we're going to, today, just a general introduction just from one of my PowerPoint notes, and then tomorrow we'll start delving into the workbook itself on 5.1, page 185. But for today, just introduction to EMR. So what is EMR? EMR stands for electromagnetic radiation. So electromagnetic radiation is our general term for light. So generally speaking, when you think about light, you might just be thinking about that visible section, that Roy G. Biv, that red, orange, yellow, green, blue, indigo, violet. But it's not. Light includes radio waves, which are invisible, microwaves, which are invisible, infrared, then that visible light, ultraviolet, X-rays, and gamma. And again, all of these, other than the visible light, we cannot see. It's interesting to note that other animals, such as dogs, do have a range into the infrared that they can see, and slightly into the ultraviolet, so it's a broader range. But a lot of people think dogs are colorblind. They're not, or cannot see color. They are kind of like a red-green color blindness. So instead of red and green, they'll just see shades of gray. But they do have the necessary neurons and the cones which are necessary to see the other colors of light. So this going from the right to the left, going from the longest waves, lower energy, and up is backwards from the way I generally draw it. But I was just noticing that at some of my son's university notes that they're going this particular order. So it's good to be able to look both ways at it. Long waves here, short waves here, low energy, high energy, low frequency, high frequency. So as you move from radio, you get shorter waves, you get higher energy, higher frequency. Very important to have that in mind. So EMR. EMR is light, both visible and light we cannot see. EMR has both wave and particle properties. So one of our major principles in Physics 30 is this wave-particle duality. It takes into account both the wave properties that light behaves like sometimes, and the particle properties. This historically was a big debate. Some very, very great physicists like Isaac Newton said, no, light behaves as particles. Others have come back and said no, waves, and back and forth until we now understand it has both properties. We're going to explain that model somewhat coming up the next day or two. So EMR travels as a packet of pure energy called a photon. These, where the packets are pure energy, they have no mass, but because they're a packet, that's what gives it the particle-like properties. EMR propagates, allows itself to self-propel by perpendicular electric fields and magnetic fields. The direction of the electric field is perpendicular to the direction of the magnetic field, which then is perpendicular to the direction that the photons are traveling, the direction of their propagation. But these electric fields and magnetic fields are always changing. It's a changing electric field which produces a new changing magnetic field. Then that new changing magnetic field, because it's changing, produces a new electric field. And then the new electric field produces a new magnetic field, and so on and so on. I'll see that here in just a second. Remember that when you go back again to gravitational fields are produced by stationary masses. And we looked this year at stationary charges producing a constant electric field. But it was a moving at a constant speed, charge that produces a constant magnetic field. But all EMR, all light there is, whether it's visible or invisible, is always caused by an accelerating charge. There's a question, whatever the form that our final exam is going to take. Right now, I'm thinking it's going to be 4 separate unit finals, and we'll talk more about that as we get closer to the end, and see exactly what the government's going to let us do on that. But this would be a question on there, guarantee it. What is it that causes EMR? It'd be a multiple choice question. Okay. They like that we can, as a Physics 30 student, keep all this straight as well as what is it that is producing gravitational fields, electric fields, magnetic fields, and what is it that is producing electromagnetic radiation. EMR. All EMR is produced by an accelerating charge. So that's cut and dried. That's going to pretty much be our mantra that we kind of listen to and obey. Accelerating charges may be, but remember what acceleration is. It might be speeding up, or it might be slowing down, or it might be going at constant speed, but it's changing direction. So if it's going at constant speed in a circle, it's still accelerating and producing photons as we go along. One accelerating charge will always produce 1 photon of light. So for every 1 accelerating charge, we get 1 photon. An accelerating charge produces a changing magnetic field. So when that charge starts to accelerate, if it was going at constant velocity, it would be a constant magnetic field. But because it's accelerating, it produces a changing magnetic field. The changing magnetic field is what induces a changing electric field. And then that new changing electric field going to 0 up to a max and then fading back down to 0 is going to produce a new magnetic field. And then that new magnetic field again is going to produce a new electric field, then that electric field, a new magnetic field, and so on and so on and so on. So it's these perpendicular. So I'm making this hand motion with my hands right now, where I've got my right hand going in a wave motion up and down, and I've got my left hand going in a horizontal motion perpendicular to that. That's the symbol for that propagation of EMR and the way that it takes place. Here's our entire EMR spectrum. You notice that this is starting on the other side from that earlier one. We've got the longest waves over here, radio waves. So radio waves 10 to the 3,000 meters. So some radio waves are a kilometer or longer. And then it shows moving across. There's sometimes some overlap, you'll notice. So the next shortest waves after radio waves are microwaves. So microwaves are very important for us in a lot of ways. It's not just making your popcorn or reheating your leftovers in microwave oven. All of our communications that we use in terms of cell phone, so they are all done with microwaves as well. So very important for us. Then we get into the area which we call infrared. So infrared, infra means lower energy than red light. Used, very important again, are your standard remote control that you use on a TV set or other remotes that have to be line of sight. If you block it, then it can't work. Those are infrared. If you do, however, have a remote control that you can change the channel on your satellite system from a different room, that's going to be in the radio wave. So sometimes they're in the radio wave, sometimes they're in infrared. In here we've got those visible that we can see. On the other side of the visible light are ultraviolet. Ultraviolet, those are the black lights that they used to use back in discos back in the 70s. If you've ever been to played laser tag at West Edmonton Mall or gone through that little Galaxyland train and all the bright colors, your dandruff, your teeth and everything brighten up, that's because they're shining ultraviolet light on you. Also used for some hydroponics growing operations as well to speed up growth. I know it's on Leonard Street, when you walk down the street, a gentleman has some UV lights in his front window where he is lighting up some of the plants that he's growing in his living room. So the ultraviolet, they are dangerous. This is the reason you wear sunscreen in the summer. It's not the visible light. The visible light does not. It may tan your skin a little bit, but it's not going to give you a really bad sunburn or possibilities people worry about in terms of skin cancer. That's the ultraviolet. So ultraviolet that we get is in this longer, this very, very high energy of ultraviolet. Fortunately, our atmosphere does filter that out. Otherwise, we'd have problems. But when we live at high altitude, like in Grand Cache. It's good to wear sunglasses when you're driving all the time to filter out those ultraviolet rays. Interestingly enough, my glasses that I often wear do tint automatically in the sunlight, but they will not tint inside, because when you get outside to the sunlight, that's where the ultraviolet is. That's what activates the tinting operation in them. When you're driving your car, they don't tint because your windshield will actually filter out some of the UV as well. After ultraviolet, the next shortest waves, but next highest energy, are the soft X-rays. So the soft X-rays, those are the ones that we're going to use when we get to this range for when you break a bone or you go to the dentist and things like that. So these X-rays, are they dangerous? Yes, especially if a woman is pregnant or for a little baby who can have those, their cells, their healthy cells ionized by these X-rays. For a normal adult, they can have a certain number of X-rays in a year and not generally have any problems at all. And then we get into the gamma rays. Gamma rays, extremely high energy, extremely high frequency, very, very short wave. And we're going to see how these are produced in a couple of different ways in the remainder of this course. So again, the EMR spectrum that we look at, generally radio waves, microwaves, infrared, all that visible, the Roy G. Biv, ultraviolet, X-rays, and gamma. I just found out recently that indigo, and I never, what's indigo, what's violet, what's all purple to me. Indigo doesn't really exist. It was just kind of made up by Isaac Newton because he liked 7. 1, 2, 3, 4, 5, 6, 7. 7 was a lucky number, and he was a little bit into in terms of lucky numbers, so he wanted a 7th color in there, so he just kind of stuck it in. The longest waves at that end, the shortest waves at the gamma end. The lowest frequency is the radio, the highest frequency is at the gamma end. As you move across, the waves get shorter and the frequency gets higher. And then the lowest energy waves, the radio waves. So we have radio waves bouncing around here all the time. If I turned on my little portable radio, I could get some local radio stations. I could hit the button on my fire department radio and have it send a signal up to the top of Grandin and back. So we have lots of these, but we only have a small portion of them going through us, and they're very low energy. That's why the radio waves don't really hurt us. What about the high end? Well, if there's gamma rays running through here, we'd be crispy critters in no time at all. So it's interesting how this works. You can see that people worry about those cell phone signals sometimes and the possibility of them causing long-term problems. What the experts will tell you is microwaves are too low of energy to actually have any ionizing or cancer-causing effects for 99.9999% of people. But if you happen to be that one person, so possibly even these very, very low energy waves, maybe a little bit, but and I know there's a lot of urban rumors going around about cell phone signals, but they are in the microwave area of your EM spectrum. So in terms of all EMR, radio, microwave, infrared, visible, here's about the frequencies. It's less than 10 to the 8 hertz. Microwaves 10 to the 9. That's a billion hertz to 10 to 11 hertz. Infrared, 10 to the 10th up to 10 to the 14th. The visible, 4.5 times 10 to the 14, 7.5 times 10 to the 14. That's an important border for us. When do visible become ultraviolet? After 7.5 times 10 to the 14. So that's a number, that's one of the few numbers I've memorized in terms of all of this. You will be expected normally on a diploma exam to have these memorized in terms of the different ranges. This year you won't have to, but you do have to know this general progression as it goes along. So you can see again that violet would be about the 7.3, left indigo out because it really doesn't exist. So these would be the averages and your average wavelengths as you go along. Notice as frequency gets bigger, wavelength gets smaller. So around 700 nanometers times 700 times 10 to the minus 9 to 400 times 10 to the minus 9 is the range of that visible light. We'll be working with those numbers quite a bit in problem solving coming up in the next week. So radio waves. How do you produce radio waves? Well, you take electrons, accelerate them back and forth at a linear antenna. So on my little fire department radio that I carry, I've got an antenna at the top. When I send a signal up to dispatch or to somebody else in the fire department, what it does is sends electrons, it speeds them up from 0 up to a maximum speed, then slows down, stop. They turn around, they come back down to a maximum speed. And the speeding up and slowing down is what generates radio waves for us. Used for fire department communication, those Sentio responding devices we use with the smart board, both AM and FM radio stations. Or as they like to say on satellite radio, terrestrial radio stations. Microwaves. Microwaves are produced actually when you accelerate electrons in a circular motion. So inside of every cell phone and in every microwave, there is a cyclotron, a little mini cyclotron, which just sends electrons around in a constant circle, constant speed, but because they're always changing direction, by going in that circle, they do produce microwaves. Used for cell phones and microwave ovens. Infrared, IR. Produced when electrons drop down to a lower level. So this is a kind of a difficult concept to get at first. We're going to talk about this concept quite a bit between now and right to the very end of the course. It deals with the basic idea of that quantum model. So our quantum model, as opposed to our old standard mechanical model of nature, but electrons usually like to hang out in a certain energy level. If you stimulate them, they'll jump up to a higher level. So electrons, if they get exactly the right amount of energy, that's what that quantum term is all about. It's a specific chunk of, and for every different type of atom and every different type energy level within that atom, there's a different specific quanta or chunk of energy that needs to get up to the higher level. So let's say you had an electron in hydrogen, you accelerated up from the first level to the second level. It can't stay there because the lower energy level is not filled. So it has to drop back down. But to drop back down, it has to give off energy. The way it does that is to send off 1 photon of EMR. So infrared, visible, and ultraviolet are all produced that way. So all of those 3 general areas are produced by electrons dropping to lower energy levels. We're going to talk a lot about that in the future. Where do we use infrared? TV remote controls. At McDonald's, the way they keep burgers warm there is to put them under a heating lamp for a short period of time. That's infrared. You'll remember from grade 7 science, and unfortunately we don't cover it in high school. No, grade 8 science maybe. No, grade 7 now. 3 methods to transfer heat. Conduction, convection, radiation. When heat itself is transferred by radiation, it's as infrared. Microwave energy does not transfer heat. So in your microwave, it's not transferring heat like the way that your standard oven is in terms of radiating heat downwards or upwards. What microwave does is it just speeds up the molecules within an object, which causes them to heat themselves. It's those faster molecules moving. So infrared cooks from the outside in, and microwaves from the inside out. But are infrared used for keeping burgers warm, or sometimes to hatch chicks in nurseries? Instead of having the mother hens sit on the eggs, they'll have those heating lamps on them. Those are infrared. So again, the Roy G. Biv, we still keep that eye in there even though it doesn't exist. Produced when electrons drop again to a lower energy level, the same as the infrared. How do we function with visible light? Well, we help us to read and to see stuff and do all kinds of cool things that we do. So we've got lots of devices in our world to help produce visible light so we can see stuff. Ultraviolet, produced again when electrons drop to a lower energy level. Those black lights that they use in different places. It's what produces your sunburn and possible skin cancers. It's what activates those tinted glasses. And again, ultraviolet can be, well, there we go, be very dangerous at the high frequency, the high energy, and especially when we're very fortunate that the ultraviolet is filtered out by our atmosphere to a high degree. X-rays. Produced when high-speed electrons stop quickly when hit a metal or glass target. So when you go to the dentist and you get an X-ray, what they do is they have a set of charge plates which accelerate electrons from rest up to very, very high speeds, and then they shoot them into a target. A target's generally made of metal, but sometimes glass, and it makes the electrons stop very quickly. It's that stopping that produces X-rays. So in the old days, in the old CRT TVs, that we used to have, the ones with the big long back in the back, not the flat screens. Parents used to say, don't sit so close to TV, you're going to give off X-rays. It really did. Not very much, though. Used to check out our teeth, broken bones, things like that. And then there's gamma rays. The gamma rays produced by some type of radioactive decay and by the collision of two antiparticles. And we're going to see that, both of those situations later in Unit 4 when we talk about radioactive decay, and we talk about the antiparticles of electrons bombarding into their antiparticle, which is the positron, and how they totally annihilate and go from particles into 2 photons of gamma. Extremely dangerous, protected by shielding, distance, and limiting time of exposure. So we do generate gamma rays with nuclear decay in a lot of different things that are in the backs of trucks running all over Northern Alberta. It's used in road building in terms of soil density gauges. It's used sometimes in the oil rig for drilling, so they can find depths that they're drilling down to, and some other things. So lots of radioactive material. How do we shield against them? Well, we shield with thick lead inside the cases that they come in. We keep a distance from them if they're loose, and we limit the amount of time that we're exposed to them to keep ourselves safe. So that's it for this one, folks. Have a good one.